for 8085 processor, so if we try to look into the machine language, so it is an 8-bit microprocessor as we have said previously. So, this is basically, so the word size is 8-bit. So, the number of different combinations that it can understand is 2 power 8, that is 256. So, you can have at most 256 different instructions with 8-bit word size. Out of that, 8085 uses only 246 different bit patterns. So, remaining 10 patterns are not used at all to form its instruction set, and these 246 patterns, so they define altogether 74 instructions. So, when I say 74 instruction, like add is an instruction, subtract is an instruction, move is an instruction, load is an instruction, like that. And depending upon the operand of the instructions may change. Like if I have got say 10 different registers in my processor, say R1 to R10. So, add R1 comma R2, so that the R1 gets the content of R1 and R2, sum of R1 and R2 is different from the instruction add R3 comma R4, where R3 gets the content of R3 and R4, sum of R3 and R4. So, that way these two are taken as different instructions. So, if we consider that way, then there can be 246 different patterns, and that correspond to actually 74 different instructions, and it is very difficult to enter the bit patterns correctly. So, they are usually entered in a hexadecimal format instead of binary format. Like suppose if you look into this microprocessor kits that are available, for the development kits that are available. So, there are two ways in which you can load your program into that kit. One is by means of having some upload facility from some computer. So, that way the values may be uploaded directly into the RAM of that processor of that kit, or many times the kits they have got a hexadecimal keyboard on which the numbers 0 to F they are given, and you can type in the values that you want to enter, like and they are entered in a hexadecimal format. For example, if you consider this particular bit combination like 00111100. So, this is actually the instruction that corresponds to the, that is it is actually corresponding to the instruction which tells the processor to increment the number in the register called accumulator. There is a special register called accumulator in 8085, and this particular bit combination 00111100, if it is executed, so it is telling the processor to increment the content of that accumulator by 1. So, instead of entering 00111100 as a binary bit pattern, so if you are entering the value through hexadecimal keypad, then the value 3 and C they can be entered, and this essentially translates to that. Of course, if you are doing it via some computer, then it will happen automatically. So, automatically the values will be loaded there, but all these uploading tools, so they have got an option which is to list the content of this uploaded file. So, there it will show in the hexadecimal format only for the sake of compactness. Okay. And all the manuals and everywhere you will find that they are talking in terms of these hexadecimal values and not in terms of binary values, because of the very simple reason that binary values remembering them or instructing them becomes difficult. And you see there are only 246 different combinations. So, in older days people almost used to memorize like what are the codes for all these instructions. So, it was not that difficult, like once a person is doing the 8085 programming for some days, it often becomes almost common to remember the instructions that are used very frequently, the codes for them. So, that way it is that was the way it was done. Now, so while we are writing programs, so one possibility is that we write the program in say high level language like C or C++, and then we have got a translator that will translate it into the machine language of the processor. Now, the difficulty is that there are many scope of unoptimized translation. Okay. So, or the translation which are not very optimized. So, and as you know that the human beings, so they are the best optimizers. So, if the a code fragment is reasonably small, and if you are an experienced programmer, then possibly you can write the best possible program in machine language, or so that you can write a program in machine language which will be better than any other program which is written in C or C++, because you will be able to calculate like the time required for executing each and every instruction and things like that, as we will see. So, that way it becomes easier or it becomes better if you write in a machine language, but again writing in machine language the difficulty is the codes and all that. Okay. So, what is done, an intermediary to these two, the high level and the machine language, is the assembly language. So, instead of entering instructions in a hexadecimal, so you can do it using some symbolic codes. Okay. So, it is so, and also if you are given a set of hexadecimal values, so it is difficult to understand the meaning of the program. So, that is the other issue. So, what is happening is that, so the companies, they have defined some symbolic code for the instructions. So, these codes are called mnemonics. Okay. A mnemonic for each instruction is usually a group of letters that suggest the operation to be performed. So, the based on like move is a mnemonic, add is a mnemonic. So, that way it is telling the operation that we want to perform. So, this assembly language program or assembly language statement, so they will consist of the mnemonic and the operands that will be there on which that operation will be done. So, if we go back to the previous example, like this particular bit pattern 00111100. So, this is 3C in hexadecimal. So, and its corresponding mnemonic is INR A. So, INR is the increment register. So, IN is increment and R is register. So, increment register A. So, A is a special register that we have in 8085, which is the accumulator. So, increment register A, and this 3C value. So, this is called the operation code, that is it will tell the processor what is the operation to be done, and that is why it is called op code or operation code. And this A, so this is called the operand, and this INR is the opcode. Now, so for example, if you take say this instruction 10, this particular bit sequence 10000000. So, this is 80 in hexadecimal. So, 80 is the mnemonic. Okay. So, 80 is the opcode, you can say, and it means that the corresponding mnemonic is add B. So, add B is the mnemonic, 80 is the opcode. So, it says that add register B to what? So, it does not tell anything like that in this instruction, but implicitly it means that this B value, the value of register B will be added to the value of register A. So, A is a special register which is called accumulator register in 8085, and whenever you have got any arithmetic logic operation, then one of the operand in most of the cases is the accumulator, and also the destination is the accumulator only. So, when you execute the instruction add B, what it will do? It will add the content of register B with the content of register A, and the value will be stored in register A. So, that the final value will be kept in register A only, or the accumulator only. So, it is important to remember that a machine language and its associated assembly language are completely machine dependent. So, like when you are talking about the C language, a high level language like C, that is machine independent. You can take the same C program to a number of platforms where the underlying processors are different, and then you can again compile it there and get it the compiled program executed. But you cannot take the same compiled code from one machine to another machine until and unless the environments in both the system, both the computers are exactly same, including the processor that you have, and particularly the processor that is exactly same. Otherwise, the machine language of one processor is different from the machine language of another, and assembly language is also different. So, assembly language is nothing but a user standable version of the machine language. Okay. So, human understandable version of the machine language. So, it is going to be different for different processors. So, one program written in assembly language of processor A will not work on processor B. So, this is a typical example, like Motorola, it has got an 8-bit microprocessor called 6800, and 8085 machine language is different from that of 6800. So, is the assembly language. A program written for the 8085 cannot be executed on 6800 and vice versa. So, that is obvious. So, for an assembly language program, so see, assembly language is also not understandable by the processor. So, for assembly language program, so we need to convert it into machine language. So, how do we do this? So, there can be two different ways by which it can be done. So, previously it used to be done by something called hand assembly. So, as I was telling, so older designers of 8085 based systems, so they remembered the code of for each and every instruction, and also if you look into the manual pages of 8085, so that will tell you like what are the codes for various instructions. So, first you write down the program in assembly language, and then look into that chart where it has got for every instruction the corresponding machine the corresponding machine instruction format, or the opcode part, opcode forms, and using those opcode, so you can convert your program it's in 8085 assembly language to the machine language program. So, that is not very difficult. So, this is done by the hand assembly. This process is known as hand assembly. So, the programmer translates each assembly language instruction into its equivalent hexadecimal code or machine language, and then the hexadecimal code is entered into the memory. So, this is the way the hand assembly used to be done, and naturally this is error prone, like while doing this operation. So, I may be doing some mistake in selecting the in looking into the proper mnemonic and all that, and there may be a mistake, and possibility of error is more, and then those entering that hexadecimal program into the computer system, that becomes another headache. So, that way it is becoming it is error prone. So, the other possibility is that a program they use a program called assembler. So, this assembler program is just like the compiler. So, compiler they translate high level language program to machine language, and these assemblers they can convert the assembly language program to machine language. In fact, if you look into any compiler, so they will be having one stage called assembler. So, no compiler translates a program directly to machine language, it converts it into assembler, and from the assembler it will be converted into machine language. The reason is very simple, like in a computer system, if I support a number of high level languages, and then individual compilers they can convert to the assembly level language program for that processor, and in the system I can have a single assembler, and that single assembler can now convert all these assembly language programs into machine language. So, there is no point in duplicating the effort of putting the assembler as a part of all these compilers. So, assembler part is made separate, and these compilers, so they generate code up to this assembly level and from that point onwards the assembler takes up and does the thing. So, this way we can have there are assemblers that are available, there are many assemblers you can find they are available, and they are used in the assembly process. So, next we will go into the 8085 microprocessor architecture. So, it is a 8-bit general purpose microprocessor. So, let us try to understand the meaning. 8-bit means, so it does 8-bit operations at a time. So, most of the operations that it does is on 8-bit data, and even if it operates on 16-bit, so it will be handling them as 8-bit data only. It is a general purpose. So, it is not a special purpose thing. For example, if you are looking into a say digital signal processor, so that is dedicated for signal processing application. So, it is not like that. So, it is a general purpose processor, and it is a microprocessor. So, it has got the CPU, it is actually a CPU consisting of ALU, then you have got registers and all that, but it does not have memory and all that with it. It is capable of addressing 64 kilo of memory. So, and each is and it is 8 bit. So, whenever it is accessing memory, so it will be in terms of 8 bit. So, that way you can say it is 64 kilobyte of memory can be addressed by the processor. Now, whether the system will have 64 kilobyte of memory or not, that depends on the designer of the system that uses this 8085 as the basic processor. Now, if it is not using 64 kilobyte, maybe the system has got only 32 kilobyte of memory in it. So, remaining spaces will be empty, and processor should not generate addresses in that range during execution of any program in that system. Anyway, so the basic processor, it has got the capability to address 64 kilobyte of memory. Physically, it is a 40 pin chip. So, there are 40 pins, and so this detailed pin layouts we will see. 5 volt power supply is required, can operate at a clock frequency of 3 megahertz, and it is upward compatible, that is the previous version 8080, it is compatible with that in terms of pin layouts. So, this diagram is actually telling us the pin diagram of 8085. So, we have got this VCC, which is the power supply pin, then we have got this X1 and X2. So, in which we have to connect a crystal externally to generate the clock signal. So, this is the frequency generator. So, this will be connected to this X1 and X2. Then we have got some special lines. So, some of the special lines that we have is, as I said, that it can address 64 kilobyte of memory. So, if it is accessing 64 kilobyte of memory, then I need 16 address bit lines, 2 power 16. So, you see these lines marked pin number 21 to 28 marked as A8 to A15. So, these are the 8 bits, and this pin number 19 pin number 19 to this pin number 12. So, they are actually the other bits. So, this is AD0, AD1 up to AD7. So, they are multiplexed address data bus. So, we will understand this multiplex term later, but this will also provide the address line. So, address line, the address bus is total 16 bit, out of that this side I have got 8 bit, and this side I have got the 8 bit. VSS is the ground, and then there are, so next, so after address bus, so we have got the data bus. Okay. So, data bus is also given by these lines. So, AD0 to AD7. So, if you just ignore this letter A, so what you get is D0 to D7. So, this is actually the data bus. Okay. So, address and data, they pins, so they are mapped onto same pins. Okay. So, address 0 and data 0, they are put on the pin number 12, address 1 and data 1, they are put on pin number 13, etc. But that actually reduces the size of the chip, okay, because you cannot have any arbitrary sized pin package. Okay. So, after so this 40 pin package is a standard package. So, after that the number of pins, next one I think is 64. So, that way in between we do not have any other option. So, it is mandatory that we keep the pin size compatible with the packaging. So, that is there. Now, apart from this, so there are some special signals like this read bar and write bar, which is for the read and write operations. So, they are to be connected. Then there is a there are a set of interrupt lines. So, if you want to interrupt the basic operation of this processor from the outside world, you can use this line. So, trap, RST 7.5, 6.5, 5.5, INTR. So, these lines can be utilized to telling that processor that something exceptional has happened in the outside world and it should take care of that. Okay. Some for example, maybe this line, say this RST 7.5 lines is connected to a mouse, and whenever this mouse is clicked, so it tells the processor that the user has pressed the mouse button once. So, that way it can, the microprocessor may do some special action corresponding to that. So, we will come to that those things later. Then apart from that, we have got this ALE signal. So, this ALE signal is address latch enable. So, that will tell us like when this that will be useful for separating out this multiplexed address and data bus lines. We will see it slowly. Then there is another line which is IO stroke M bar. So, IO M bar, so it is input output or memory. So, when this processor is connected to some memory device, it can also be connected in a similar fashion to some IO device. Now, when it is processor is accessing the accessing outside world, it is accessing for outside world for some data. So, whether the data is from memory or from IO device. So, if it is from IO device, in that case this IO M bar line, so this value will become 1, and if it is from the memory, then this IO M bar line will be equal to 0. So, accordingly we can design some decoder circuitry by which either the memory chip will get enabled or the IO devices they will get enabled. So, we will discuss slowly on all these concepts. So, this diagram gives a cleaner way of understanding like what are the things that we have. So, we have got this higher order address bus A8 to A15 in pins 21 to 28, address and data bus. So, they are multiplexed. So, this AD0 through AD7. So, they are multiplexed here at this. So, this address and data bus, and we have got this. So, your crystal is connected here between pin 1 and 2. Pin 40 is the plus supply voltage 5 plus 5 volt. Pin 20 is the VSS, which is the ground line. Then you can have some interrupts. So, like given by the pin number 6, 7, 8, 9 and 10. So, they are the interrupt pins. Then you can have some interrupt acknowledge. So, this is this INTA bar line. So, this is pin number 11. So, this comes in conjunction with this pin number 10 INTR. Okay. So, this INTR, so this when this interrupt is coming, so this interrupt acknowledgement pin is activated by the processor. So, when we will discuss on the interrupt, so we will be talking about this interrupt and interrupt acknowledge pins. Now, so in my board, so apart from the processor or the microprocessor, there can be many other devices that also need a clock signal. So, this clock out pin, so this is actually giving the clock signal of the processor to the other components on the board. So, if you need any device to be driven by the same clock as the microprocessor, so you can use this clock out line for that purpose. Similarly, there is a reset pin. So, this reset in bar. So, if this reset in bar, so this line is made 0, that means this 8085 operation will be reset, and as a result, so processor will start operation from the beginning. So, some registers in the processor, they will get some special values that in some sense will mean that the processor is restarting the operation. And as similar to the clock, this reset also we may need to give a reset out, because when this reset pin is activated, maybe we may have to reset many other devices as well. So, that is the reset out pin. So, this reset out will be this signal can be used to reset other devices. And we have got this SID and SOD. So, these two lines. So, this is SID stands for serial input data and SOD stands for serial output data. So, if you are feeding values to this microprocessor from the outside world, so one possibility is that you put some IO device connected through this address bus data bus lines. Okay, that is one way of doing it. The other way of doing it is you have some serial you have some mechanism by which you can send the bits serially and they are connected to this SID line. So, the bits are coming serially. Similarly, this microprocessor can serially output the data through the SOD line. So, if you are satisfied with low speed data transfer, you can go for the serial communication via this SID and SOD line. Okay. Another important pins that we have, this read bar and write bar. So, this read bar and write bar, so they are actually the read control and write control. So, this will tell whether the processor is trying to read from the outside world or it is trying to write to the outside world. So, when it is say trying to read from the memory, then this read bar line should be made 0, that is it is active. So, it is read bar. So, 0 means it is active. So, this read bar signal is activated, and if it is trying to write something onto the memory, in that case it is the write bar signal will be activated. So, instead of memory it may be IO device also, and whether it is IO device or the memory. So, that is identified by this IO M bar line. This IO M bar line, as I have said, if this line is equal to 1, that means the processor is expecting the value to come from some IO device, and if this value is 0, then it is expecting the value to come from the memory. Then these two pins S0 and S1, so they actually tell the stage at which the microprocessor is at this point of time. So, as you know that this processor executes the instruction by following this fetch, decode, execute cycle. So, in those phases this S0, S1 pins, so they will have some appropriate values. So, by looking into these values from the external world, so you can understand what the processor is doing now. So, this S0, S1 and this IOM bar, read bar, write bar, these signals, so they tell about the status of the processor, and they are in general known as the control and status signals, because that talk about the status of the microprocessor. So, if we are looking into the wires that we have in the system, so that gives rise to something called system bus. So, this is the wires that connect the memory and the IO devices to the microprocessor. So, address bus is unidirectional and it identifies peripheral and memory location. So, if you look into this address bus, so this address bus you can see the A8 to A15, it is going out from the processor, and similarly here also this when this multiplexed address data bus acts as address bus, then it is going outside, going out of the processor. Okay. So, this address bus is unidirectional and it is going to the outside, output from the processor, and it is used for identifying the memory location from where the value has to be read or where the value has to be written, or the peripheral device that has to be accessed for doing the operation. Then the data bus, so data bus is bidirectional, because you may need to transfer the value from the microprocessor to some memory location or IO device, or you may have to get the value from the memory location or IO device to the processor. So, as a result this data bus is going to be bidirectional in nature, and there is control bus. So, they are for synchronization of synchronization signal, timing signal, control signals, etc. So, they are actually constituting the control bus. So, the system bus, it is consisting of all those wires which constitute the address bus, data bus and control bus.